In 2026, the industry is witnessing a strange phenomenon. Despite having large language models that are exponentially more capable than their predecessors, enterprise software delivery speeds have plateaued. This is the productivity paradox. While simple code generation has reached near-instant speed, the overhead of integrating that code into massive, interconnected microservices has become a new bottleneck. We are seeing a massive surge in verification debt, where human developers spend 80% of their time fixing subtle logic errors introduced by AI assistants that lack a holistic view of the entire system architecture. The traditional one-one pair programming model, where one human guides one AI, is no longer sufficient for the scale of modern development requirements. If you continue to treat AI as a simple autocomplete tool, your team's velocity will eventually hit zero as technical debt accumulates faster than it can be managed. But what if the problem isn't the AI's intelligence, but the way we organize the work? By the end of this lecture, you will discover the blueprint to break through this ceiling by shifting from individual assistants to orchestrated autonomous units. This is the only way to survive the complexity of 2026 development cycles. Now, let's look at the shift in the management paradigm itself. To move past this plateau, we must shift our perspective from managing prompts to orchestrating workflows. In the 2026 landscape, the most successful teams don't just use one AI. They deploy a fleet of specialized agents: an architect agent to define the structure, a coder agent to implement logic, and a critic agent to perform rigorous security and performance checks. This transition requires a fundamental change in the developer's role, moving from a line-by-line coder to a high-level orchestrator and system designer. We are no longer just writing code with an AI. We are managing a digital workforce that follows a strict collaborative protocol. This shift allows for autonomous operations where entire feature sets can be drafted, tested, and refined before a human even sees the first PR. However, building such a team is not just about connecting APIs. It's about defining roles, managing shared context, and establishing verification gates that prevent agentic hallucinations. Are you ready to stop being a pair programmer and start being an orchestrator? This paradigm shift is exactly what we will explore in detail. But first, we need to understand how we got here. Let's examine the evolution from simple assistants to autonomous units in the next chapter. Imagine it's 2026. You are still typing prompts into a chat box for every single function. This one-on-one interaction, once hailed as a revolution, has become your biggest bottleneck. The cognitive load of constant context switching between your intent and the AI's hallucination-prone draft is draining. In the field, we see senior engineers spending 70% of their time babysitting code suggestions rather than architecting systems. This is the death of simple pair program. The old model of human-in-the-loop for every micro-decision creates a synchronous dependency that cannot scale with the complexity of modern distributed systems. To break this, we must shift toward an asynchronous, objective-driven model where the human defines the what and why, while a swarm of agents handles the how without requiring constant hand-holding. But how did we get trapped in this babysitting loop in the first place? Let's look back at the trajectory. In 2022, GitHub Copilot introduced autocomplete on steroids. By 2024, tools like Devin and OpenDevin attempted to handle entire tasks, though they often struggled with long-term memory and complex repository contexts. Now, in 2026, we've moved beyond general-purpose assistants to custom agent units that are deeply integrated into a company's specific domain knowledge and CI pipelines. These agents aren't just predicting the next token. They are executing shell commands, browsing documentation, and performing self-correction within a sandbox. This evolution shows a clear trend. The abstraction layer of software development is moving higher, from lines of code to task objectives. If you are still evaluating agents based on their ability to write a single LeetCode solution, you are missing the bigger picture of autonomous workflow integration. Is this evolution purely beneficial, or is there a hidden cost to this autonomy? A prominent CTO recently noted that managing a fleet of AI assistants has become a full-time management job for developers, ironically reducing actual coding time. This is the management trap. When you treat an AI agent as a junior dev that needs one-on-one mentoring for every line, you haven't gained a teammate, you've gained a dependent. In high-performance environments, the shift is now toward outcome-based management for AI. Instead of reviewing every line during the generation process, teams are setting up automated validation gates, LLM-based reviewers, and robust unit test generators that act as the first line of defense. This allows the human developer to act as a director rather than a line manager. Without this shift in perspective, your productivity will continue to plateau regardless of how powerful the underlying model becomes. But what does a team of these outcome-based agents actually look like in practice? The core of the 2026 autonomous unit is specialization. We no longer use a single do-it-all agent. Instead, we deploy specialized roles. The architect agent analyzes the system requirements and defines the interface. The developer agent implements the logic, and the quality agent generates edge case tests and security audits. This is swarm intelligence applied to SDLC. By decoupling these roles, we prevent the jack of all trades, master of none problem inherent in large monolithic models. Each agent can be optimized with specific system prompts, RAG data, and even different fine-tuned models tailored for their specific task, like using a high-reasoning model for architecture and a high-speed model for routine boilerplate. This division of labor mirrors a high-performing human team, but operates at a speed that is orders of magnitude faster. However, even the best team fails if they all try to solve the same problem at once. So how do we split the work? The final piece of the puzzle is task decoupling. In traditional pair programming, the task is monolithic: build this feature. In an autonomous AI team, we use a recursive breakdown process. The orchestrator receives a high-level objective and decomposes it into parallelizable subtasks. For example, while one agent is updating the database schema, another is drafting the API documentation, and a third is building the front-end component, all based on a shared contract defined by the architect agent. This parallelization is where the true 10x productivity gain resides. We move from a sequential waterfall-like chat to a concurrent execution flow. This requires a sophisticated state management system to ensure all agents are working on the same context without drifting into conflicting implementations. Mastering this decoupling is the difference between a chaotic AI mess and a streamlined production engine. Now that we understand the unit, it's time to look at the glue that holds it all together: the architecture of agentic orchestration. In the fast-evolving landscape of 2026, simple prompt-based coding is considered a relic of the past. We have entered the era of Spec-Driven Development 2.0, or SDD. The core failure point for most AI pair programming efforts today is ambiguity in intent. SDD 2.0 solves this by moving away from chat boxes and toward executable specifications. These are not just documentation, they are structured, machine-readable contracts written in Markdown or YAML that define strict requirements, edge cases, and architectural constraints. In a multi-agent environment, these specs act as the single source of truth that prevents agents from drifting into hallucinations. Think of it as a formal blueprint where every line of natural language is backed by a technical schema. Professionals in the field now spend 80% of their time refining these specs rather than writing the actual code, because the spec is the code. But how does this static document actually trigger a full-scale development cycle? The answer lies in the automated pipeline that follows. Let's trace the flow from a high-level specification to a finished pull request. In the Spec-to-PR pipeline, the orchestration engine parses the SDD 2.0 file and breaks it down into granular tasks. This isn't a linear process, it's a recursive cycle. A project lead agent analyzes the spec and delegates modules to worker agents. For example, if you're building a microservice, one agent handles the API layer while another manages the database schema, all coordinated by the central spec. This pipeline integrates directly with Git-based workflows. Every change is logged, and every task is mapped back to the original specification requirements. By the time a pull request is generated, the AI has already verified that the code aligns 100% with the provided specs. It's a leap from asking for a feature to orchestrating a factory. However, running this sophisticated factory requires a specialized infrastructure: the 2026 Agentic stack. The Agentic stack of 2026 is no longer just an LLM and a prompt. It is a multi-layered ecosystem designed for autonomy. At the base, we have the inference layer, often utilizing specialized models like GPT-5 or Claude 4 tailored for code. Above that is the context management layer, using RAG to feed the agent the entire codebase history. Crucially, the verification engine layer now uses specialized domain-specific languages, DSLs, to validate logic before a single line of code is committed. We are seeing a move towards sandboxed environments where agents can execute code, run benchmarks, and profile memory usage in real time. This stack enables autonomous units to operate without constant human hand-holding. If your team is still using a single agent IDE extension, you are already falling behind the state-of-the-art orchestration standards used in leading tech hubs. But wait, with so many moving parts, how do we prevent these agents from creating a chaotic mess of conflicting code? When multiple agents work on the same codebase, conflict is inevitable. This is why the master architect pattern has become the industry standard for orchestration. In this hierarchy, the master architect agent doesn't write code, it manages the state of the project. It acts as the ultimate arbiter, resolving merge conflicts and ensuring that a change in the authentication module doesn't break the payment gateway. It maps out dependencies in a dynamic graph, identifying which agent should wait and which can proceed in parallel. Conflict resolution in 2026 isn't just about accepting incoming changes, it's about semantic reconciliation. The master architect understands the purpose intent behind the code and merges logic, not just text. This hierarchical structure is what allows a team of 10 AI agents to outperform a traditional team of human developers. But coordination is only half the battle. We still need to verify that the output actually works. Verification in an autonomous world is driven by self-correction loops. Gone are the days when a developer waits for a CI/CD pipeline to fail. In 2026, agents operate within an automated testing gate. Before presenting any code to a human, an agent must write its own unit tests, execute them in a container, and fix any bugs it finds. This is the inner loop of agentic development. If the tests fail, the agent analyzes the stack trace, reflects on its logic, and iterates. This self-correction capability reduces the noise that reaches human reviewers by nearly 90%. We are moving toward a zero-bug policy, where the agent is physically unable to submit a PR that hasn't passed a comprehensive suite of auto-generated tests. It sounds like a dream, but there is a catch. This leads us to a critical question: if the agent is writing the code and the tests, who is checking the validity of the tests themselves? The most dangerous hidden cost of AI orchestration is what we call verification debt. As agents become more autonomous, humans tend to trust their outputs blindly. But if an AI hallucinates a test case that passes against hallucinated code, you have a catastrophic failure waiting to happen. The core challenge of 2026 is: who verifies the AI's verification logic? To manage this, we implement verification gates where a separate, adversarial agent tries to break the code written by the primary agent. We must also maintain human-in-the-loop checkpoints for high-risk architectural decisions. You cannot simply delegate responsibility. You can only delegate tasks. If you don't manage your verification debt, the speed gains from AI will be wiped out by the technical debt of unverified logic. We've seen how the architecture should look, but does it actually hold up under pressure? In the next chapter, we look at the brutal reality of 2026 benchmarks and the common failure modes that break even the best orchestrated teams. In the software landscape of 2026, we are no longer debating whether AI can code. We are measuring how fast it can disrupt the entire development lifecycle. When comparing traditional human teams to autonomous agentic swarms, the data is staggering. While a human-centric team might have a cycle time measured in days, balancing meetings, manual reviews, and context switching, an orchestrated AI team operates in a realm of minutes. However, the defect rate metric tells a more nuanced story. While AI teams produce code at 10x the throughput, the initial defect rate can be higher without a robust orchestration layer. Real-world observations indicate that the human-in-the-loop model currently maintains the highest quality-to-speed ratio, but the gap is closing as multi-agent validation loops become standard. We must look beyond the raw speed and analyze how these metrics shift when we remove the human bottleneck entirely. But velocity is a double-edged sword. What happens when that speed creates invisible technical debt that no human can keep up with? Let's examine a critical enterprise case study from 2025-2026 involving a Fortune 500 financial firm that transitioned to agentic orchestration. The SWE-bench 2026 results show a massive leap in agentic resolve rates, with top-tier orchestration frameworks solving over 65% of end-to-end issues without human intervention. In this enterprise case, the company utilized a multi-agent critic model to handle legacy COBOL to Java migrations. The data revealed that while the coding agent could translate syntax perfectly, the architectural agent was required to prevent massive memory leaks caused by context-blind translations. The success wasn't found in the AI's ability to write lines of code, but in the orchestration layer's ability to cross-reference legacy documentation with modern security standards. The transition led to a 40% reduction in total cost of ownership, TCO, for legacy systems, but only after they implemented rigorous validation gates to catch agent hallucinations. Data shows success, but it hides a catastrophic failure mode that happens when agents lose the big picture, which we will dissect next. What happens when the dream team of AI agents becomes a nightmare? We call this a hallucination swarm. This occurs when agent A makes a slight error in an API assumption, and agent B, rather than checking the truth, takes that error as a grounded fact to build a secondary service. By the time agent C tries to integrate the build, the entire system is built on a foundation of context drift. In a documented failure case, a swarm of agents hallucinated a shared library dependency that didn't exist in the enterprise's private registry. They successfully faked the implementation in tests, passing all local checks, only to crash the production build because the runtime environment lacked the hallucinated package. This highlights the echo chamber effect, where agents validate each other's mistakes rather than referring back to the source of truth. It is a terrifying example of how high-velocity orchestration can accelerate disaster if the observer agent is also compromised. So how do we draw the line between helpful autonomy and a dangerous lack of oversight? As we push toward full autonomy, we enter the danger zone, the point where the cost of verifying AI output exceeds the cost of just writing it from scratch. In the field, we see that unsupervised autonomy works brilliantly for isolated tasks like unit test generation or boilerplate scaffolding. However, for complex business logic, the technical debt grows exponentially after the 80% autonomy threshold. This is because AI agents currently optimize for local completeness rather than global maintainability. To survive this, tech leads must pivot their role from master coder to orchestration auditor. You must implement supervised autonomy where agents are allowed to propose changes, but a human-led orchestration gate must verify the long-term architectural impact. Without this, your 2026 project will be a house of cards, ready to collapse at the first major version upgrade of an underlying LLM. Benchmarks prove AI can code, but they don't prove AI can think like a tech lead, which is exactly what we will tackle in our next chapter on strategic judgment. In 2026, the dream of an infinite workforce often collides with the reality of the token economy. When you deploy a multi-agent swarm consisting of a planner, multiple coders, and specialized reviewers, the cost for a single medium complexity feature can skyrocket. If each agent performs multiple reasoning cycles using high-tier models like the successors to Claude 3.5 or GPT-4, you are no longer just paying for an API. You are paying an agentic tax. I have observed enterprise projects where the compute cost per PR exceeded $50 due to recursive self-correction loops and massive context window consumption. As a tech lead, you must calculate if this agentic cost truly offsets the total cost of ownership compared to a human developer. It is not just about the invoice. It is about the reasoning to value ratio. If your agents are burning thousands of tokens just to fix their own hallucinations, you are effectively subsidizing a broken workflow. But wait, financial cost is only the visible part of the iceberg. What about the hidden cost of technical debt and architectural drift? Next, we examine the human side of this equation. The role of the developer has fundamentally shifted from author to editor-in-chief, leading to a dangerous psychological trap, the illusion of competence. When an autonomous team of agents delivers a 1,000-line diff that passes all green light CI tests, the human lead often falls into the rubber stamp trap. We must ask, who watches the watchers? If your agents are reviewing each other's code, they might be reinforcing the same architectural biases or overlooking subtle race conditions that their training data failed to account for. In 2026, the most critical skill for a tech lead is no longer knowing how to write the code from scratch, but having the auditing stamina to challenge the AI's output. If you stop being the ultimate gatekeeper, your codebase will eventually become a black box that no human on the team understands. This leads to a terrifying realization: are we building systems, or are we just managing ghosts in the machine? This risk is why a specific implementation strategy is required, which we will unveil in the next section. To survive the 2026 landscape, you shouldn't choose between all human or all AI. The answer lies in the orchestrated hybrid model. In this framework, the human lead acts as the architectural anchor, defining strict interfaces, schemas, and constraints before a single agent starts its task. The AI agents are then constrained within sandbox execution environments where they can iterate rapidly on business logic, but they are strictly forbidden from modifying core architectural scaffolding without explicit human approval. Think of it as a human-guided swarm. By implementing human-in-the-loop checkpoints at the specification phase and the final integration gate, you maintain 100% architectural integrity while gaining 10x implementation speed. This ensures that the high-level design remains human-readable and maintainable for future generations. This hybrid approach is the only way to scale without losing control of your system. But how do you know if your specific project is actually ready for this level of automation? I have a checklist for that. Before you flip the switch on an autonomous AI team, you need a reality check. Based on current industry patterns, I have compiled a 5-step readiness checklist for 2026. First, is your test coverage above 90%? Without a robust, automated safety net, autonomous agents are a liability, not an asset. Second, do you have machine-readable documentation like OpenAPI, protobuf, or detailed ADRs? Agents fail when they have to guess your intent. Third, is your CI/CD pipeline capable of agentic rollbacks, the ability to automatically revert and quarantine agent-generated code? Fourth, have you established token budgets per team to prevent runaway costs? And finally, your team culture ready to transition from being makers to orchestrators. If you check all these boxes, you are ready to lead the next generation of software engineering. This is the end of our strategic overview, but the most important question remains: as AI takes over the how, what happens to the human why? In the final chapter, we will look at the redefined future of the engineer in an AI-dominated world. In the landscape of 2026, the primary metric for a professional developer is no longer lines of code written, but the robustness of the orchestration logic governing autonomous agents. As we have explored, simple pair programming is merely the entry point. To survive this shift, you must master the multi-agent lifecycle, from defining specific personas for LLM agents to implementing automated validation gates using tools like Agentic for schema enforcement and LangGraph for stateful multi-turn logic. You must transition your mindset to that of a lead system architect who directs a specialized fleet of digital workers. You are no longer just writing functions. You are designing the verification loops that prevent agent hallucination in mission-critical production environments. This transition requires a deep understanding of prompt engineering 2.0, where prompts are treated as compiled logic rather than simple chat instructions. By focusing on the system rather than the syntax, you position yourself at the top of the value chain where human judgment remains the final arbiter of quality and security. This is the only way to move from being a replaceable coder to an irreplaceable orchestrator who can manage complex agentic workflows at scale. But even with these technical skills, there is one final strategic insight that separates the top 1% of engineering teams from those who will be left behind by the AI wave. The ultimate competitive advantage in the 2026 landscape will not belong to those with the fastest LLM, but to those who possess the most sophisticated orchestration framework within their organization. While most teams will still be struggling with the basic friction of 1-1 AI pair programming, elite teams will be operating at the autonomous team level. In this model, the ratio of human engineers to AI agents might reach 1-10, shifting the focus entirely toward the agentic workflow maturity model. Teams that successfully integrate automated unit testing, security scanning, and architectural reviews directly into their multi-agent pipelines will achieve a release velocity that was previously thought impossible in traditional software engineering. Remember, the core goal of orchestration is to minimize human intervention debt. If your agents require constant manual correction, your orchestration logic has failed. However, if you can build a self-correcting loop of specialized agents, you unlock a level of exponential productivity that redefines the profession. The future of the engineer is to be the pilot of a high-speed digital fleet, steering the vision while the autonomous agents handle the mechanical complexity of implementation. This marks the end of our lecture series, but the real implementation starts the moment you open your IDE and start defining your first multi-agent orchestration workflow.